Okay, thank you very much for this very wonderful workshop. Sorry that I can't be there in person, but hopefully you'll get something interesting out of this talk. I will tell you about the unitary limit, two-component, four-component Fermi gases, and the connection between cold atoms and nuclear physics. So here's my outline. I will first talk about the computational method we use, which is lattice effective field theory. Then I'll talk to you about some calculations of two-component Fermi gases at unitarity. Then I will ask the question, is nuclear physics near four-component Fermi gas unitarity? And then I will talk about some results relating to the carbon-12 spectrum and structure. And then I'll summarize. So the technique we use is lattice effective field theory, which is we put protons and neutrons on a lattice with a lattice spacing of 0.5 to 2 Fermis or so. But of course, if we're doing cold atoms, and these are just the atoms, and so the lattice spacing would be something quite different. So what we can do with the lattice effective field theory for nuclear systems is we can probe the strongly interacting phase diagram. So here I'm showing you the density on the horizontal axis, and here is the saturation density of nuclear matter, the density of nucleons in an iron nucleus. And here is the temperature in megaelectron volts. And so if one does simulations using lattice QCD, you can probe essentially up to infinite temperatures, but there's an angle here beyond which you cannot exceed because of complex phases that appear in the lattice simulations. But if you change your degrees of freedom to protons and neutrons, you can actually go to higher densities at colder temperatures. But there's obviously a limit to which you can go in density and in temperature. That is when the nucleons overlap with each other, so that you have to work with a quark and gluon degrees of freedom, or if the temperature is high enough that you excite states that are not in our effective theory of the strong interactions using protons and neutrons. But so what we do with this is we try to understand what's going on at low energies. We have this effective theory of the interactions of the nucleons. And so here's some effective potential between the nucleons. We have at leading order some contact interaction like a delta function interaction between the nucleons and the exchange of a pion. But then beyond leading order, we have next to leading order interactions like two pion exchange and higher derivative contact interactions. And this is what's called chiral effective field theory. So what we do is we then tune up the unknown coefficients of this interaction to reproduce what's seen in the laboratory. For example, here are the phase shifts we get at about 1 Fermi lattice spacing. And here are the phase shifts for the spin singlet S wave, the spin triplet S wave. So what we're doing is we're matching the coefficients to reproduce what's seen in the laboratory. The laboratory data is the solid lines, and the colored bands are showing you the uncertainties of the lattice calculations at various orders in the calculation, at leading order, next to leading order, next, and N3 alone. So the reason we do all of this is so that we can do many-body simulations. So to do the many-body simulations, though, we use Euclidean time projection, which is essentially taking the exponential of minus h tau, where tau is large. And so you can think about this as a low-energy filter that we kill the high-energy states, and the low-energy states remain. Now, the Hamiltonian H contains a term that looks like the kinetic energy, and so that's minus del squared over 2m. So if I exponentiate that, plus del squared over 2m times tau, that gives me a diffusion operator. So I can think of the particles as diffusing in space as a function of time. So this can be modeled exactly as a random walk in space as a function of Euclidean time. So you can think of these particles as executing some random walk in space as a function of time. At the same time, they're having these interactions from the potential of the interaction. Okay, so we have short-range contact interactions, as well as in the case of nuclear physics, the exchange of pions. All right, but the way we actually do the calculation, though, is using auxiliary fields, we write down the interactions, which I showed you. Might have a contact interaction like n Dagrange squared, and we have to do things like the exponential of minus c over 2 n Dagrange squared. So we can then rewrite this in terms of an auxiliary field S integrated from minus infinity to plus infinity. So we have the exponential of minus 1/2 s squared, and this term that's linear in S and linear in n Dagger n. So to do this integral, you know how to do this integral. You complete the quadratic form, and the term that's missing is exactly this term here. So once you integrate over S, you get exactly what you have in the top line. The square root of 2 pi cancels the 1 over square root of 2 pi. And you have then the fact that instead of having a two-body interaction between two particles, you have a one-body interaction interacting with this auxiliary variable S. So we can remove the interaction between the particles, and we can replace it with interactions of each particle with the background field. And we do this for every point in space and time. This is what's called a Hubbard-Stoyanovich transformation, or just the auxiliary field transformation. Okay, so instead of having the nucleons or the particles interacting with each other, they interact with the auxiliary fields. And so now we can write down the single nucleon matrix of amplitudes. So if I have A particles, then I have an A by A matrix of single particle amplitudes. That's a function of the auxiliary fields and the pion field. Then we calculate the full amplitude by multiplying together the single particle amplitudes and anti-symmetrizing, and that gives us the determinant of the single particle amplitude matrix. Okay, so now let me talk to you about some results. So let's suppose we're considering what's called the unitarity limit. So we consider S-wave two-body scattering in 3 dimensions at low momenta. Then the scattering amplitude is 1 over p cotangent delta minus IP. And then at low momenta, we can do an effective range expansion of p cotangent delta in terms of the scattering length A0 and the effective range R0. But now if we take the scattering length to infinity, then at low momenta, we can make this approximation that p cotangent delta is approximately equal to 0. And so then the scattering amplitude in the S wave is proportional to I over p. And so there's no fundamental scale in this system. And so we get scale invariant physics, which means that there's some very nice conformal symmetry properties, scale invariant properties of this 2-component Fermi gas at unitarity. So let's consider then this non-relativistic 2-component Fermi gas tuned to the unitarity limit, so that the range of the interactions is 0 and the scattering length is infinite. So as I mentioned, there's no intrinsic scale, so everything should be proportional to the relevant power of the Fermi momentum Kf. Now for energies and temperatures, there's also this overall factor of the inverse particle mass. So if I then take a system with the interparticle spacing of d and the ground state energy of E0, and if I to rescale this system so that the interparticle spacing is d prime, then I have this very simple scaling relation between E0 and E0 prime, that E0 d squared is equal to E0 prime d prime squared. So now then I can say what is the particle energy per particle of the system. So this conformal symmetry, the scale invariance, is actually a feature of the free Fermi gas. So if I talk about the energy per particle for the free Fermi gas, it's 3/5 times the Fermi energy. And so for the unitary limit, the energy per particle is going to be some parameter you typically call the Birch parameter Xi times the answer for the free Fermi gas. So they're just this constant proportionality. So we can do some calculations of what is this Birch parameter. So there have been several other calculations that have looked at this as well. So this was the first, I would say, very careful calculation done by lattice simulations by Carlson, Gandolfi, Schmidt, and Zhang in 2011. We did some calculations more recently, taking 66 particles. You can define actually this ratio between the unitarity limit and the free Fermi gas limit in various different ways, either using the free Fermi gas thermodynamic limit result or the actual energy for a finite system. You do it 2 different ways, and they don't disagree by very much, by about 1%, but you can see that it's about 0.37 or so, taking the continuum limit as you take the lattice spacing relative to the particle separation, the lattice spacing going to 0. Okay, and that's in good agreement with has been seen by the MIT group.
Da läuft eins, aber das ist langweilig für mich im Moment.
Yeah.
Nuclear Physics to Ultra Cold Atoms.
Ist das eine Konferenz?
Das ist ein Workshop.
Help me maybe mute.
Mikrofon ist an.
Yeah. Thank you. Okay, so in this unitarity limit, we're looking at this crossover between a BCS, a Bardeen-Cooper-Schrieffer state, and a Bose-Einstein condensate of molecules. So the unitary limit is somewhere in between. So you can ask the question, what are the properties of the superfluid? So you can measure them, the two-body density matrix, where you annihilate two particles at one location and you create them somewhat far away at these primed locations. Okay, so then as the pair where you annihilate and the pair where you create are separated by a long distance, and you get this factorization, that you have this pairing wave function phi between R1 and R2, and phi star between R1 prime and R2 prime. And then there's this factor here, which is the condensate fraction alpha times the number of the total possible maximum number of pairs, which is n over 2. And so this is going to, you'll see this in the limit that the separation between the unprimed and the primed coordinates goes to infinity. So we've done this calculation on the lattice with the 66 particles, and we can see this long range order in the two-body correlation function. And so we can then extract what is the superfluid condensate fraction. And what we get in the continuum limit is that alpha is about 0.43 with an error of 0.02, which is in pretty fair agreement with what's seen by the MIT group, Chiral in 2004, which got about 0.46 with an error of 0.07. We can also take a look at what this pairing wave function looks like. So we can write down an ansatz for the pairing wave function, which looks something like a Yukawa function. That's the behavior you expect for an S-wave bound state. And so if we then try to figure out what this length scale zeta is, zeta p, for the pair, we find that zeta p is about 1.8 h bar over k Fermi, over the Fermi momentum. Okay, so at this point, I'm going to make it a hard transition and ask the question about going beyond two components. So we know that in the unitarity limit, there is also interesting physics that happens when you go beyond two components. But in this case, what happens is that quantum mechanics and quantum field theory, let me just read what I say here, that scale invariance is often spoiled by quantum scale anomalies, and that's actually what happens in this case when you have more than two components. And so what you get is the Efimov effect when you have 3 or 4 component unitary limit. So instead of seeing conformal symmetry, you see this broken scale invariance broken down to this discrete scale invariance. And you see then bound states that are forming a geometric series in terms of their binding energies. And so you see this factor of about 515 or so in energy between the various repetitions of the trimers. And so for each Efimov trimer, you also have these Efimov quadrimers. You actually have two Efimov tetramers for each Efimov trimer. So this is all beautiful physics, and there's many people in this workshop that have worked on such physics like this. But the question I'm going to focus on today is whether nuclear physics is near the 4-component Fermi gas unitarity. Okay, so there's been several papers that have asked this question, nuclear physics around the unitary limit, led by Koenig and collaborators. So they essentially took a look at nuclear physics as a perturbative expansion around this unitary limit point. Then there was also this paper more recently by one of the workshop organizers, Alex's group, together with this student, Will Dawkins and Joe Carlson and Bira van Kolk, where they took a look at the 2-alpha system or Brillouin 8 and to see what happens in the 0 range limit there. So I'll address some of these questions about whether nuclear physics is close to the unitarity limit for 4-component Fermi gases. So to address this, we took a look at two different interactions at leading order in chiral effective field theory. And to make a long story short, we just basically took these two interactions that had one pion exchange and some short range interaction and Coulomb potential. The difference between interaction A and B resides in the short range interaction. So for interaction A, we took a non-local short range interaction. And for interaction B, we took a non-local plus a local short range interaction. Now, I should explain what nuclear physicists mean by local. So when I say a local interaction, I mean an interaction that is diagonal in position space, like the Coulomb interaction. It has no velocity dependence. If I write down the actual interaction kernel, it's completely diagonal in position space. Whereas a non-local interaction would have some off-diagonal pieces to it in position space. So now what's surprising is that these two different interactions, A and B, look the same for the two-body system, the three-body system, and the four-body system. But once we did the 4+4 system, or two alpha particles, or the 8-body system in S-wave scattering, what we found was that B was reproducing what you would see experimentally, empirically, for the alpha-alpha S-wave scattering phase shifts. Here you see the results for B in the squares compared to the empirical results in the asterisks. And so this is with Coulomb. But for A, when you put in the Coulomb, you actually find that you get something that's much closer to zero. Essentially, you can shut off the alpha-alpha interaction. So what we found here is that there was a dependence on whether the interaction was local or non-local, as well as what the range of the interaction was. And so we could actually induce then a phase transition in this theoretical calculation of nuclear physics. So by making an interpolation between interactions A and B, A on this side and B on this side, we could actually go from a Bose-Einstein condensate of alpha particle gas of alpha particles to nuclear liquid. So there's this point here where the alpha-alpha scattering length with the Coulomb interaction turned off, with the alpha-alpha scattering length is equal to 0. And so then if we have enough nucleons, if we have enough alpha particles, it will form and it will gather together and form a liquid. Then if we go a bit further, we then will have bound finite systems. And then at some point, we will have the alpha-alpha system or the Brillouin-Mate system being bound. And that's the unitarity limit for the alpha-alpha scattering. Okay, but what's interesting is that that there is this proximity to this quantum phase transition, suggesting that that in fact nuclear physics is not quite that close to the unitarity limit for four-component Fermi gases, but there's a dependence on the details of the short-range interaction, that the locality of the interaction and the range of the interaction is important. So we actually then took a closer look at this. And so we asked the question, what is the minimal nuclear interaction? What is the simplest nuclear interaction that can reproduce the ground state properties of light nuclei, medium mass nuclei, and neutron matter with no more than a few % error in the energies and charge radii? So we constructed an interaction with only 4 parameters. And the first 3 parameters were tuned to the two-body system, the 2-nucleon system, and the 3-nucleon system. So these are the strength of the 2-nucleon S-wave interaction, the range of the 2-nucleon S-wave interaction, and the strength of the 3-nucleon contact interaction. So these 3 parameters were tuned to two-body scattering and to the 3-body system, the 3-body binding energy. And then with 1 extra parameter, that was the range of the local part of the 2-nucleon interaction, we tuned to everything else. Okay, and so that with those 3 parameters tuned to the 2 and the 3-body system that are shown here, and with everything else tuned, with only 1 parameter tuned to everything else, you can see that we get a fairly good reproduction of the binding energies of nuclei up to about 48 particles. So here's the mass number, the number of nucleons, and here's the binding energy. And here are the predictions with this very simple interaction. So you can see that nuclear physics, although it's not close to the unitary limit for 4-component Fermi gases, it is close to this other limit, which I will now tell you about, which is called the Wigner-SU4 limit. So the Wigner-SU4 limit was something that was observed by Wigner about 90 years ago or so. He noticed that there was this approximate symmetry for the low energy nuclear interactions, where you think of the proton spin up, the proton spin down, the neutron spin up and neutron spin down as 4 components of an SU4. And so this interaction here that we use had an exact Wigner SU4 symmetry, except we added some Coulomb interaction to take into account. So this is this has this SU4 symmetry. It's not the unitary limit because the range of interaction plays some role, but it's not that far away from the unitarity limit in some sense. Okay, so you can see some of the properties of this SU4 symmetric theory plus the Coulomb interaction. So here's the binding energies for the triton compared to experiment, helium-3 compared with experiment, helium-4 with experiment, oxygen 16, neon 20, magnesium 24, silicon 28, carbon 40, as well as the charge radii. And you can see this SU4, very simple SU4 theory does a fairly good job of that. And you can also take a detailed look at what the charge distributions look like. And here with Coulomb in the blue squares, you can see a good agreement with empirical charge distribution versus the radius, the charge density. So the empirical results come from electron scattering. You can see also the calcium 40 is doing relatively well. The central densities may be a little bit above the empirical results, but it's pretty good for this very simple interaction. Now, in the remaining 5 minutes or so, I'm going to tell you a bit about the structure of carbon-12 using this very simple interaction. So here's a spectrum that you can reproduce of the carbon-12 low-lying states. So the notation here is the 0 means spin 0, the 2 means spin 2, obviously, and the plus is the parity, and the subscript on the bottom here is just the numbering from the bottom, the lowest being number 1. And so you can see there's a fairly good reproduction with different lattice spacings with the experimental results. Okay, this is work from last year, but we actually, this is work done by Shihang Shen in Jülich, postdoc with my colleague Ulf Meissner. And we took a closer look at this again more recently this year and tried to understand the structure of all of these states of carbon-12. And so here are the older results in the pentagons and circles. The stars are the experimental results in black, and the squares are the new results that we've done. This includes 3-body interactions now. And the symbols here, the triangles that are either equilateral or obtuse, actually are showing you the actual structure of the states, which I'll now show you in a moment. So from these simulations, we can actually reproduce the intrinsic shapes of these carbon-12 low-lying states. And the surprising thing is that there seems to be 2 general structures that you can see. One thing I should mention from the outset is that you see alpha clustering in all the low-lying states of carbon-12. So carbon-12 obviously has 6 protons, 6 neutrons, 12 particles overall, but these carbon-12 states like to cluster into 3 alpha clusters of 4 particles each. And what's interesting is that in the ground state, we get this equilateral triangle. That's the ground state. And there's a rotational band that comes from the various rotational excitations of this ground state, the first 2+ state, and here's the first 3- state. But there's also this famous state that's called the Hoyle state of carbon-12 that's actually responsible for the abundance of carbon being produced in large in red giant stars in our universe. That enhances the triple alpha reaction because the Hoyle state sits close to the triple alpha threshold. And the Hoyle state has this rather interesting structure where it has this kind of bent arm configuration with an angle of about 140-ish degrees, something like that. And you can see the different angles. Here's a plot of the angles between of this triangle. Here you see 60-60 for the ground state, and for the Hoyle state, you see a much larger angle here. And what's interesting is you can see the rotational band on top of the Hoyle state. So here's a second 2+ state, but you also see there's a third 0+ state, which is another slightly different configuration, but also has this rather interesting obtuse triangle or bent arm configuration. So you can go on and look at all the other states of carbon-12, and you can see in some cases the alpha cluster structure is not quite so clear. But still, you can see there are some centers to these alpha clusters. So here are some equilateral triangle configurations, which also have a dual description in terms of the nuclear shell model. But you can also then see some more exotic configurations where we have the 2- state and the 1+ state, 4+ state, and so on, which have then this bent arm configuration or the equilateral triangle configuration. So let me now summarize. So we started with an introduction to lattice effective field theory. Then we discussed the unitary limit and properties of 2 component Fermi gases at unitarity. Then we talked to systems with more than 2 components and asked the question whether nuclear physics is near the unitary limit. We found that symmetric nuclear matter is near a quantum phase transition, suggesting that the unitary limit for nucleons is likely produces a Bose gas of alpha particles rather than a nuclear liquid. However, we found numerical evidence that nuclear physics is close to Wigner's SE4 symmetric limit, with alpha-alpha scattering near the unitary limit. We then discussed the intrinsic structure of the low-lying states of carbon-12. Thank you very much for your attention. I'm very happy to answer any questions.
Very much. Do we have questions indeed?
Hi, it's Piotr Magierski.
Hey, Piotr.
Hi, I would like to ask about possible conclusions for, well, possible implications for neutron-proton pairing versus neutron-neutron and proton-proton pairing. So can you comment on that on the basis of your calculations?
Yes, certainly for the light nuclei, for like carbon-12, there's this approximate SE4 symmetry, and so the proton-neutron pairing is indeed important. Now, as we go to heavier systems, there is going to be, you have more neutron-rich systems, and obviously the neutron-neutron pairing, proton-proton pairing will be a bit stronger. But we do know that the proton-neutron pairing does play some role in, for example, in understanding deformations and such relating to spin-orbit couplings and things like that. But there is definitely some neutron-proton pairing.
Thank you.
Hello, Michael Urban from Orsay.
Okay.
I have a question about the quite large lattice spacing that you are using in these calculations. So what you have just shown, I think there was a lattice spacing of 1.9 Fermi or something like this. So I think this is more than 1/2 of the wavelength of Fermi wavelength at saturation density. So I wonder, how can you describe a nucleus that in its center reaches more or less nuclear saturation density?
Sure. That's a great question. So here I show you some results. This is actually with a 1.3 Fermi lattice spacing. The 1.9 is I would say too big, but we do most of our calculations at 1.3 Fermi lattice spacing. So what you'll see here, though, is that we reproduce the charge density with quite good fidelity. You'll notice the 1.3 Fermi sits about here. And so you might ask the question, how is it that we can get resolution that's much smaller than our lattice spacing? And there's a very simple answer to this question. It's because the center of mass of the nucleus does not sit on a lattice site. If I have A particles, it sits on a lattice site divided by A. So in other words, you get lattice spacing resolution of the one-body densities. And so that's actually why we see all of these effects here. Now, in terms of what lattice spacing is sufficient, 1.3 Fermi lattice spacing, I would argue, corresponds with the momentum scale, a sort of momentum cutoff scale of about 450 to about 500 MeV. So it is actually very similar to the ab initio calculations done with that sort of a cutoff scale. So it has comparable accuracy in terms of cutoff effects.
Hi, here is Sandro Stringari
Yeah, Sandro.
from Trento. And you mentioned about the two-spin unitary Fermi gas. The possibility of calculating the pairing, the pair superfluid fraction, which fits quite well with experiments. What about the superfluid density at finite temperature? Can this quantity be calculated? Because I didn't see any systematic calculation about this quantity.
Yeah, so the calculation I was doing was at 0 temperature, and so this is not maybe so interesting, but yeah, the finite temperature superfluid fraction would be quite interesting. I have not done this calculation though. The calculations at finite temperature cold systems are quite challenging though. Going directly to 0 temperature, you have the ability to do projection Monte Carlo calculations with some initial state and final state, and that helps to make the simulation easier. But the finite temperature simulation, you have to take a trace of states, and then when you get very cold, this is a more difficult calculation. It can be done, but we have not done it.
Okay, thank you. There are still questions.
Hey, Dean, it's Neil Warrington.
Hey, Neil.
Hey, I'm wondering about your Wigner SU4 interaction. Is what you mean by that the interaction with those 4 bullet points? Or
Yeah. This is what's going on. So the S-wave interaction does not care about spin or isospin. It's SU4 symmetric. That's the main point.
got it. So in bullet point number 3, how exactly do you tune the strength of the 3 nucleon contact interaction? Like what observable do you tune that to?
We just simply tune it to the triton binding energy.
Got it. And is there some, I don't know, fancy Hubbard-Stratanovich that you use to deal with the 3 nucleon contact interaction, or how do you deal with that?
Yeah, so it depends on what we are doing. In this particular paper, you can read. So here's the paper. It was led by my postdoc at the time, Bingnan Liu, and he used a discrete Hubbard-Stratanovich transformation, which allowed him to tune this 3-body contact interaction.
Got it. Thank you so much.
Sure, no problem.
Some more questions? Do we have questions online?
Yes.
Yes, please.
Hi, Dean, this is Thomas. Very
Hey,
nice
Thomas.
talk. I wonder, the essential ingredients to nuclear binding seem not to include pion exchange.
Yeah, it's because we are, yeah, this is a great question. And so how important is pion exchange is probably your question, right?
Right.
Yeah. So we know that pion exchange is the dominant mechanism for the spin orbit splittings. And so the deficiencies of this interaction, you can see as I go along the isotopic chain, it's not reproducing the physics quite right. And so there are shell closures, subshell closures that are described by spin orbit interactions, which come from pion exchange, the tensor force of pion exchange. And so we do see now that we are able to do these calculations using some new techniques that I'm not describing in this talk, we do see the improvement coming from the tensor force. So we can reproduce all this, but better with the 1 pion exchange.
Thank you.
Sure.
Okay, more online questions?
So
No?
I have one. Dean,
yes, please, Alex.
Yes. And it's in connection also with the cold atom crowd, right? So you went from 2 components to 4 components. What about 3 components and the connections with, so essentially, you can have nuclear physics with 3 components, right?
Yeah, that's a great question. So now 3 components is obviously the most difficult for us because we use pairing channels to remove the sign problem in the auxiliary field Monte Carlo calculations. 3 components is just an awful sign problem. Obviously, because there's no pairing channel, that we have fermions that would like to form in the liquid, and so they're frustrated in some way. But with other techniques that can deal with the sign problem there, it would be interesting to explore for sure.
And there's no way of kind of like having 4 components, but freezing one or something?
Yeah. The problem is that if you have 4 components, you benefit from the pairing symmetry if it is symmetrical. Once you freeze it or just remove the 4th component, then you destroy that symmetry and you don't get any protection from it.
Okay, thank you.